Right, up to your time.
Hey, cool. Hey everyone. Good morning or whatever, wherever you are in the world. So today the session is going to about reinforcement learning algorithms in deep generative models, and I'll take DeepSeek as an example. I gather that the audience here, some of you are from CS 236, the generative model class. Some of you are from CS 234, reinforcement learning. So I'll try to cover the concepts of both reinforcement learning and large language model first, and then we'll see some interesting ideas, how they are combined together. Yeah, let me share my screen. So I had this note. I'll share this afterwards as well, because I find this easier to put down all the formula and the graphs. But basically, now I think um, generative model, or in this session, I'll focus on large language model, RLHF, or reinforcement learning with human feedback, has really become a routine in large language model training. So for example, from OpenAI in 2022 and also Anthropic, they have been applying RLHF in their large language model training to really improve the model quality, the response quality, and also maybe in order to align the model in terms of safety or integrity. And in DeepSeek, the DeepSeek R1 is, I think it really impressed the industry because it applies RL in a larger scale, and the DeepSeek R10, it uses reinforcement learning on a pre-trained large language model, and they observed that the large language model pick up some of its own reasoning capability out of reinforcement learning. So that's really a uh, quite impressive moment. But for example, there have been also debates like this tweet from Andrej Karpathy. So Andrej, he was in OpenAI a while ago, and he is also sharing a lot of interesting ideas. This tweet, I think it was from maybe 1 or 2 years ago as well. Basically, the TLDR is RLHF is just barely RL. It doesn't think RLHF is true reinforcement learning, which, in a sense, after the talk, maybe you'll come to your own conclusion. Yeah, so let's get into it and take a look at how RL plays a role in the current LLM training. Um, so the agenda for today, I'll cover some basic RL concepts and some LLM concepts, and then we can go through the training paradigm in DeepSeek and some interesting observations of applying RL in DeepSeek R1 training. Yeah, so to start with about reinforcement learning. Reinforcement learning has been really interesting in a way because it's unsupervised. All you need is you train the model, and by providing it with the reward from the environment, and the magic happens and the model just learns how to behave correctly. So in the past, maybe I can make it just a little bigger. So this is a very basic paradigm of reinforcement learning. A few key concepts in it is we have a state, which is what the agent can observe up until now. So let's take AlphaGo as an example. So in a game of Go, where really RL has impressed the world, like it was maybe 8 years ago already. In a Go game, the state is on the game board. What is the current state? And an action is the agent's possible move. Like in Go, it means where the agent wants to place the stone. And for reward, it is a feedback signal. So in the game of Go, um, the most intuitive cumulative reward is in the end, whether the agent wins the game or not. But there could also be other designs, for example, providing reward in the process. So overall, the workflow is the agent is probably a neural network we want to train. It observes the space and gives an action based on the state. And then uh, the environment, it will give a reward based on the action the agent makes and also moves to the next state as t+1. And throughout this process, so the state, action, and reward, uh, they are the variables we can think of. And there are functions that connect these concepts together. So for example, policy function, this is something that's going to be important and we cover the most about. The policy function is taking the state and predicts what the next best action would be. So it's a probability distribution over the actions given the current state. So you can think of like in Go, the policy function tells us how to place the next stone. But in, let's say, large language model, the policy function, you might notice that this is similar to the autoregressive model, where given the prefix, the large language model predicts what's the probability for next token. Value function, it gives us an expected reward given the current state. So you can think of this as given the current state, like in the end, how likely we will probably win the game. So in the game of Go, so given the current state, like given the current state on the board, and if we play out in the end, what is the possible outcome? And it gives us an expected value of whether we are going to win the game or lose the game. So the value function takes the state as an input and returns a value. For Q function, for Q function, it takes it kind of it can the kind of enhancements from the value function. So it's predicting the expected return, not only based on state, but both the state and action. So you can see how value function and Q function, they are closely related to each other. For value function, it's basically summing over all the possible Q function values given all the actions that might take. So the value function is basically the expected value of Q function over all the actions. And we have the reward function where given the state and action, it tells us what is the reward. So yeah, if you're from the reinforcement learning class, I guess you're quite familiar with all this. But basically, we have the state, action, and reward, and our goal is to get a policy function. We want some kind of policy to guide us what action to take, and we're trying to maximize the reward. And the reward, we define it as this J function. So given the policy that we're going to take, and let's say we play out the game till the end, R is the reward. We get the total reward throughout the trajectory, and we want to train our policy to maximize this cumulative reward J function. So there are quite a few different approaches in reinforcement learning. For example, there are value-based function that we try to learn the value function or the Q function. And when we want to select the action, we just look at the V function and Q function to see which action leads to the best value or Q value in the next move. Or we can directly optimize the policy. These are called policy-based method, where in some methods, we have both a policy function and a value function. It's called actor critic. This is if you are from CS236, this is a little bit similar to the GAN structure, the generative adversarial network, where uh, we have a policy that gives an action that generates the action, and also a critique, which in this case, it would be the value function to judge whether the action is good or not, and they are trained altogether at the same time. Um, so RL in the beginning, like before a large language model comes out, and RLHF seems to be all about large language model. RL has been used to, for example, in AlphaGo to play games, and there have been like OpenAI Gym, the Atari games, these kind, or even robotics like planning things. These are where RL was applied to in the first place, like including PPO. So here I include PPO as an example to RL algorithm. PPO is proximal policy optimization. So if you look at its paper, PPO, I believe it's being used by OpenAI to do RLHF in at least GPT-3 or 3.5. But when it was first proposed, if you look at the paper of it, it was used to play Atari games, to do this cart pull movement in this kind of playground environment instead of using it on a large language model. Um, but to basically combine the concepts we have, like the reward we want to optimize and all the actions and policies, PPO, the PPO algorithm tries to optimize the policy directly. And if we look at the gradient, so we basically want to optimize the reward, and we take the gradient of it so that we can do gradient ascent in this case, since we want to optimize this. You could see that we have this gradient on the policy. This policy is a neural network. In large language models case, this policy is the decoder-only model architecture. And you can see that we sample the trajectory using the policy, which means in Go, we use the network to predict the a whole gameplay, where in large language model, it is we use the model to generate a sequence of tokens. We calculate the gradient of the log of the predictions, and we have a coefficient multiplied to the gradient, which is the advantage function. So advantage function, it is the difference between the reward we get by taking action AT at ST versus the average reward we get at the state ST. So we don't have to go too deep into this advantage function. You can think of it as just the value, or you can think of it as how good the current action is. So this basically means if the token prediction is good, it leads to a better than average answer, then it has a larger coefficient to help us optimize the gradient, to optimize the policy toward. But if the action is worse than average, then we are pushing the policy away from its original value by doing the gradient ascent. So, well, this is the like a policy gradient process. You may notice that, for example, in the original definition of the reward, there's no policy. Like we don't have the pi in this expression, and we don't have log pi. If you're interested, I suggest you looking into this. For example, a blog from Lilian Wen about how we uh, how we get this formula. It's a very fundamental and important theorem in policy optimization in reinforcement learning, and it's really an interesting process because it shows how the recursive nature in reinforcement learning gets to play in here. But the takeaway for this section is in reinforcement learning, we not always, we try to optimize the policy function and we take some coefficients to help us define how big a step we want to take. If this coefficient is a constant, let's say 1, then we are optimizing the policy directly with the action we give, then it's basically supervised learning, a supervised training process. But in reinforcement learning, we get these different actions, we get these rewards by playing out the game or when we're doing the large language model inference. That's when we have all sorts of different coefficients here that help us direct the training process of the model. And so this is just the vanilla policy gradient. And in PPO, it looks a little complicated, but the idea of PPO is we want to make sure that every step we take is not too far from the original policy. That's why you see all this clipping operation and the mean operation here. So that actually tells us why reinforcement learning is being fun, but also challenging, because the reward we get could be very unstable and it could unstabilize our training process. So imagine in Go, like the whole play of Go, there might be hundreds or thousands of moves, but only in the end will we know whether the game is a win or a loss. Then in the training process, it will be the reward we get can be really unstable. For large language model generation, this is even worse because the search space for large language model is much larger and the sequence can go uh, long. Like for Go, usually question, answer, coding question, the sequence can go really long. And so a lot of these reinforcement learning algorithms, they try to stabilize the process. So this is the idea of PPO, and that's kind of it came out before large language model became a thing, and PPO was applied to RLHF, I believe in GPT 3.5. So this is all the basic concepts about reinforcement learning for now. If you haven't done reinforcement learning before, this would sounds like a lot, but the key point is that we have the policy, we have the agent, we have the state, which is the observation, and we optimize the agent by trying to optimize in the reward. And this whole process, it could be unsupervised. Like in Go, we know like in the end whether it's a win or loss, and we optimize the agent to take the actions that will lead to a win and kind of talk the agent out
Recording in
of
progress.
taking the actions to a loss. So large language model right now, it's this kind of autoregressive generative model, previous tokens, and the large language model will just predict the next token. Sorry, I was probably cut off just now. Uh, okay. Um, yeah, you can all see the notes, right? Yeah, let me know if you don't. And yeah, so on autoregressive model, like I just mentioned, notice how this, well, I mean, it's analogous to the policy function RL, but basically they are both conditional probability. They are both given some observation, we want to get the next action or the next token. And I believe you've seen this graph probably a lot already, the structure of transformer. So transformer is the uh, backbone of current large language model where um, now we only take the right half, which is the decoder part. That's why all the large language model now you might also heard that they are decoder only model, where we only have the decoder. They observe the previous tokens and predict the probability distribution of next token. A visualization here is like how this whole thing works. So the input is all the previous uh, tokens in the text sequence, and the GPT model or any large language model. It sees the previous tokens and predict the next one. So for this session, I won't go deep into like the attention mechanism and everything else, but just keep in mind that the observation of the previous tokens, they can be considered as the state in reinforcement learning. And the large language model is predicting the next token, which you can think of as the next action, as we have in RL. And RLHF is widely used in large language model training right now. Usually, the current large language model training contains following stages: pre-training, supervised fine-tuning, and also a LHF stage. So for uh, pre-training, it's also a supervised training process. This is where the large language model sees all the text data the the company has bought from vendor or has crawled from the internet just by doing the very basic maximum likelihood optimization. So we train the pre-training stage. The large language model is just to trained to predict the next token and learn from all the text data. In supervised fine-tuning, or sometimes the purpose of it is to do instruction tuning, where after pre-training oh, whoops. After pre-training, the large language model only knows to predict next tokens, but at this stage, large language model still doesn't know how to answer a question correctly. So that's why we have supervised fine-tuning, where the data scale is much smaller than pre-training. In pre-training, we're talking about trillions of tokens, but in supervised fine-tuning, it's probably just tens of thousands of question answer pairs. And in supervised fine-tuning, large language model is trained to learn how to answer the questions proposed to the user instead of just trying to continue writing what you have. So if you ever play with, uh, so after supervised fine-tuning, we get the behavior just like we have in ChatGPT. But without supervised fine-tuning, if you go play with like the pre-trained version of llama models, you'll see that the model just tries to continue writing what you have, even if you're asking a question. The model, instead of trying to answer it, is actually just continue writing your question. And RLHF is usually the final stage, trying to optimize the final bit to get some improvements, especially on some subtle areas, because um, a lot of the times to prepare good supervised fine-tuning data is very costly. So imagine we want to train the model to write poems or write a section of codes. If we want to leverage human annotators to prepare the data, it's really costly for someone to write a long section of codes that are correct, or for someone to write a poem that is good. But it's easier for human to tell, like if given two poems, which one is better, or given two section of codes, which one is better formatted. So because of this, RLHF can optimize the large language model to really gain the final reward over like writing the better poem, right? Writing the better codes that is sometimes challenging even for a human to produce. And based on this assumption, we had PPO like in the beginning, which is shown in the diagram to the left, where we collect the preference data. The preference data is usually generations from the large language model itself, and we ask human to tell us, we have these two poems, which one is better, or which one answers the user's question better. And with these preference data, we train the reward model. And then we use the reward model, like recall that we need to get a reward in reinforcement learning setup. And we use the reward model to play as the environmental reward and use reinforcement learning to train our large language model. And in DPO, which is actually proposed by Professor Hermano from CS236, it is simplified from the PPO RLHF process by removing the reward model. In this case, through some math formula, like I encourage you to read the paper, we can write the reward directly with the policy, or basically the large language model that is used to generate the tokens. And so that we don't need to train the reward model anymore. So a few interesting changes in the process that I'd like to highlight is that back then when PPO was proposed, it was used to train like humanoid controlling task, Atari games. But really when it comes to DPO, which came out maybe 2023 or 2024 even, it's already about training language models. And if you think of the DPO process, like somehow it feels like a supervised fine-tuning, like a supervised training process instead of RL. So I think that's why like Andrej could parse it that RLHF is not real RL, because the preference data they can be collected offline. So I can prepare a whole bunch of preference data, and I'm pretty much training the language model in a supervised fashion to optimize this loss function, where the data is prepared offline, and I'm just doing the policy optimization with the previously prepared data. So unlike in maybe in actual RL, the model really needs to play the games, and which sometimes is called on-policy optimization, where the data is collected while the model is getting trained. In DPO, the data is collected beforehand, and we use them to train the model in it's almost like in a supervised fashion. And now we have DeepSeek. So DeepSeek, this nice visualization is from Harry Chen, and I think it very nicely illustrates the whole training process of the DeepSeek R1 model, where like all the concepts we just mentioned, the supervised fine-tuning and RL, are captured in these blocks, and you can see that there are multiple stages of supervised fine-tuning and also reinforcement learning. So let's maybe go through this. Um, so the DeepSeek model, it starts with DeepSeek v3 base. This is a model of like mixture of expert architecture. It has 670 billion parameters in total, and it is pre-trained on a whole chunk of language data. I think it's yeah 14.8 trillion tokens. Also, they use some filling middle trick. Um, but basically, the DeepSeek v3 model is just a pre-trained traditional language model which predicts the next tokens. It does not know how to answer questions yet. It does not been through any reinforcement learning, does not know how to reasoning. So just a language model predicting the probability for next token. The first thing they do is the starting from scratch reinforcement learning, the part that is plotted with the dotted line. So they do the reasoning-oriented RL with GRPO algorithm. So GRPO we'll cover later, but uh, similar to PPO, it's just a reinforcement learning algorithm that based on the rewards trying to optimize the policy, which in this case is the DeepSeek v3 base model. Here it's called reasoning-oriented RL. I think it partly because the tasks that are focused on in this process, they are two types of rewards provided in this process, and both of these rewards are not based on human feedback or a model-based reward model. They are all rule-based rule-based reward. So one type of reward is accuracy. So in this reinforcement learning process, all the questions are from AIME competition or coding problems, where in these cases, the answers by either checking whether the codes can be executed correctly. The reward is rule-based, and there's also some formatting reward, trying to enforce the model to use these think blocks. So if the model can put a think token and wrap the thinking process between the think block, you'll get a reward out of it. So I think this process, I feel it's more like the classic RL, where like the accuracy or the formatting consistency are like the wins or loss at the end of a Go game. And there's nothing else in this process, just by looking at the results and see whether the model can figure out some interesting way of solving the problems by itself. And that actually works. What it leads to is the model DeepSeek R10. By zero, I guess it's just like alpha zero. It means it starts from scratch. It does not go through any supervised fine-tuning, but only by relying RL, it has DeepSeek R10. And with the DeepSeek R10, they use DeepSeek R10 to produce some long chain of thoughts data as a cold start training data. And they use this to do supervised fine-tuning on. So now we get into the straight line part, not the dotted line part. They use it to do supervised fine-tuning on DeepSeek v3 base. And after supervised fine-tuning, they take this model to do the reasoning-oriented RL again, plus a new reward. So this is something they observe that when they are only doing the reasoning-oriented RL, that leads to DeepSeek R10 in the end, the model produces answers that are less readable by human. Sometimes the outputs are mixed with different languages like English and Chinese, since that's the two languages that DeepSeek models focus on. So they are the mixture of language, and that's why they added in a new reward to encourage the behavior with consistent language output. And after this reward process, they get this model, the DeepSeek V3 base with reasoning-oriented RL plus the code start to supervised fine-tuning. And then there's some more RLHF. So here the rejection sampling is also a common technique used in RLHF, where they take this model and use the model to generate some outputs. And using a V3 model as a judge, they sample some data that is some outputs that is of higher quality. And to get some reasoning data. And on the other hand, there's some non-reasoning data. So the non-reasoning data are like, in the reasoning data, they focused on coding questions, math problems that can be judged by a rule-based reward model. But there's this non-reasoning data, which is like other large language model tasks about like rewriting this email, write a poem for me, this kind of non-reasoning data. They combine them into supervised fine-tuning data and run supervised fine-tuning on the base model again. And in the end, with some final RL, based on both reasoning reward and preference reward, that's how DeepSeek R1 is produced in the end. So yeah, it's a whole long process. But I think the interesting part is this first trial, the reasoning-oriented RL, that's directly run on V3 base without supervised fine-tuning, that produced R10. And afterwards, it's like training the model and generating some samples and then again doing supervised fine-tuning and then do RL again. So it's kind of a exchanging process between supervised fine-tuning and RL, then generate some data to do supervised fine-tuning again, and then RL. So a few interesting highlight. Yeah, one thing to note here is how the scale differs on different stage. The V3 base, like the pre-training stage, it consumes 14.8 trillion tokens. But when it comes to supervised fine-tuning, you can see that it's like 800K samples. We're generating 600K samples. It's in terms of thousands and barely minimum when it comes to supervised fine-tuning and RL. Yes, and that's like the basic process of how DeepSeek R1 is generated in the end. Let's briefly go into the GRPO algorithm and that is used by DeepSeek. So I would also encourage you to read the original GRPO paper, also the DeepSeek R1 paper as well, because actually their paper, I found it to be very comprehensive. They compare their methods with like PPO and DPO and really shared some insights there. You can see that they are really willing to share their insights. So for example, the reason why they use GRPO instead of PPO is that so if we look at this graph comparing PPO versus GRPO, PPO, so we have the policy model, which is the large language model itself. But in PPO, we need to train a value model together with the policy model during the training process. And usually this value model is basically the value function in the RL process. The value model usually it's initialized from uh, the supervised fine-tuned checkpoint of the large language model. So essentially this policy model and the value model, they are of the same size. They are both initialized from the pre-trained large language model. So it's a really heavy process to run inference on the value model or train it. Essentially, we are training two large language models at the same time in PPO. And um, yeah, and in GRPO, they got around this by every time when they want to evaluate the value of an action, instead of leveraging a value model, what they do is they uh, get a group of different samples, like from O1 to OG, and get the reward. And then they can leverage the reward to estimate the value on this state and action, which is basically can think of it as a uh, Monte Carlo process, like sampling multiple values and estimating the value and getting the average. So in this case, they don't need the value function anymore. And just by doing multiple samples, they can get the advantage and train the policy model. And um, so here I listed out this is the J function, the reward over the trajectory, and also the gradient of it on PPO, DPO, and GRPO. So this is actually also covered in the GRPO paper, where they pointed out a very interesting relationship between these three. So although they have different definitions, but if we look at the gradients, usually they follow the form of we have the gradient on the log policy times some coefficient. So in PPO, we have the gradient times the advantage function. But the advantage function, to get the advantage, it relies on the value model and also a KL divergence between the policy model and the reference model, and also a reward model. So for PPO, calculating this advantage is very expensive during training. For DPO, similarly, if we look at the gradient that we want to do gradient ascent on, we have the gradient on policy, and the coefficient that is multiplied to this gradient is this. It's the preference between a positive sample and a negative sample. And here, notice the difference in that for PPO, the actions are sampled from the model, the model from the previous step. But for DPO, the positive and negative samples they are sampled from an offline policy. So the data in a DPO, they can be prepared beforehand, and we calculate this coefficient, and then we do a gradient ascent. And in GRPO, we also have this gradient on policy, and the coefficient of it is an estimate of the average plus this term. This term is trying to estimate the KL divergence between the current policy and the reference policy, so that when we are doing the optimization, we won't drift too far away from the base policy. This is also one measure they take to stabilize the RL process, which is also used in DPO, where you see the KL divergence. Not that's explicit in the formula, but in PPO, we also need the KL divergence to make sure our policy model stays close to the base model. So yeah, we have the GRPO, and the GRPO is used in all the different RL stages in DeepSeek models, like when we are training R10 or the final stage. For RL, it's always GRPO. And it's more efficient in that we don't have to train two big models at the same time. We just need the policy model and um, get different samples, and then we can run the RL on it. So yeah, in the end, how well does it work? This graph shows the quality of DeepSeek R10 during training. So again, R10 is the model that starts from the pre-trained base model. It's not supervised, fine-tuned. It has never been trained to answer these questions. Here you can see how the accuracy on the math competition questions are improving throughout the time, and in the end surpasses OpenAI o1 mini. Well, usually I find it really fascinating how when reinforcement learning works, because it's like we don't need to give guidance to the model, but they just figure out how to do things correctly by just looking at the reward. And what they also real observe in the process is during the training, while accuracy is growing, the output sequence length is also growing. So that's an observation that the model learns to take more time to think. You can call it that, taking more time to think, to output more tokens, to output the thinking process, and gradually leading to higher accuracy. Especially they mentioned this aha moment in the paper as well, where when DeepSeek R10 is trying to answer the question, sometimes it says, hey, this is an aha moment I should mark here. Maybe I should think about whether this is correct. So it's having this kind of retrospective self-inspection and taking a longer thinking process and getting a better accuracy in the end. They do observe, like we just mentioned, that without supervised fine-tuning, if R10 is trained only on the reward based on the correctness of the code or of the math questions, the output is less readable and it contains a mixture of different languages. And what's interesting is that when they enforce the consistent language reward on it, they observe slight degradation in the results. So this kind of echoes a research from Anthropic that came out just recently. They try to interpret what is the thinking process within the large language model. Like usually for human beings, if I'm a native English speaker, then I'm thinking in English. If I'm a native Chinese speaker, I'm thinking in Chinese. Then what is the language that large language model, like how are they thinking? So their kind of conclusion is that large language model is thinking in these abstract tokens that are shared across different languages. There's no specific language LLM is using to think. And it's interesting to see that when DeepSeek R10 is allowed to output in different languages, it gets a higher accuracy. But if it's allowed to use only one language, maybe it somehow actually harms or impedes the thinking process. So I find it quite interesting and may reveals to us about how LLMs are working and maybe also how human brains are working. Um, and a few other details they mentioned in the paper. For example, uh, DeepSeek R10, like we mentioned, uh, when it's doing the reasoning-oriented RL, uh, there can always be the question when we are providing the reward. In their practice, it's only rewarding based on the final result, whether the answer is correct, whether the code is correct. But will it help if we provide some reward in the process? Because if we are only giving a reward till the end, the intuition is that the reward will be very sparse. Like out of all the hundreds of tokens or thousands of tokens that the large language model is outputting, it's not seeing any reward in the process. It only gets the reward in the end. So if we can tell the large language model, provide some guidance in the process, like after the large language model finishes section one, we can give a reward. You are doing good, you are going on the right path, or hey, you're probably not doing on the right path. If we provide this reward in the process, will it help? And the answer is no from their research, because uh, for one thing, it's really tricky to define the reward in the process. Uh, it's hard to say like if the LLM is answering a coding question, like after the first section, it's hard to say whether this is the good way to go or whether it is just implementing in a way that is better, but we don't know yet. So it's hard to define the reward. And also um, uh, but to provide the reward, unlike Go, where we can define some rule-based reward in the process, we have to train a model uh, to tell us, okay, given the first section of the codes, it is doing good. And given the second section of code is doing bad. And this will lead to reward hacking, which is the model, instead of trying to figure out the correct answer in the end, is just trying to trick the reward model by outputting something that the reward model thinks looks good, but actually might not end up work well in the end. So because of these reasons, they noticed that providing a model-based reward in the process doesn't really help. And it solely relies on a rule-based reward in the end about whether the answer is correct and whether the code executes correctly. Uh, yeah, I'd say that's also an interesting thing to know. Like, I guess we can read into the philosophical side of it by saying that sometimes in the process you don't really know whether you're going the right way or not. But focusing on the results probably let you learn more. And yeah, they also tried Monte Carlo tree search, which is used in AlphaGo, where for every to get the values of every action, it does Monte Carlo tree search, basically trying out different possibilities um, down the path. And in this way, it knows it has a better estimate of the current value, and it explores the space a little bit um, so that the the estimation and the policy function can get a better sense of where it is heading. But it doesn't work with DeepSeek R10 as well. Because it comes back to the question, when it's doing the Monte Carlo tree search, what is the basic unit that each state should take? Is it like every new token would be a new state? Or like what they are trying to do is every time when a large language model outputs a new block of thinking, that's a state, and they do Monte Carlo tree search based on that state. Um, so that is quite tricky to define, and it doesn't really work out in the end. they notice that the model will sometimes just get stuck in the local optima if they're doing multi-college research. And yeah, also another interesting thing is they notice that DeepSeek R1, it doesn't like few shot prompting. So in the prompt, if we provide some examples of the expected answers, it doesn't perform as well as just letting DeepSeek R1 do the thinking by itself. Um, yeah, these are more like, well, for now, I guess a lot of them are still quite empirical, and we lack the understanding of why that is the case. But yeah, I think it's interesting to see how RL is applied to a base model, to a pre-trained model, and get quite good capability on reasoning. And yeah, uh, if you haven't tried out DeepSeek, maybe you can go play with it. It's interesting to see its thinking process all printed out. Um, yeah, we only have 1 minute left, but any question from the audience or any comment, any uh, thoughts, interesting observations you have?
Can you? Yeah, I've got a quick question.
Yes.
I just wanted to confirm one thing. Um, I understand overall how the reinforcement learning works, and I understand how the LLM works, the training. I'm not quite clear of the actual connection of how the policy information is connected with the language model. Is it literally the policy is the prediction of the next token? And the two are the same, or is the connection indirect?
Yes, they are. The policy function that is trained in the reinforcement learning process is the large language model. So when you look at for example, if we use PPO to do
Yes.
RL on large language model, this policy here is the LLM.
So that's the probability of the next token for time t plus one, basically.
Yes.
Okay. The second question is I can see that you train with the reward um, using the final reward. Um, is that trait? Is the LLM, are all the weights fine tuned based on the reward, or is it a subset of the weights, or is it LoRa? How does the back propagation in the LLM actually work with the reward?
Hmm. Yeah, that's a good question. You can do both. I believe what they have in DeepSeek R10 is that the full model is trained. Like all the weights in the models are trained, and um, the back propagation is essentially like when you take this gradient on the
Mm-hmm.
policy. Um, so like you have the policy, which is the large language model, and you
Yeah.
and when you uh, take the gradient, it back propagates to all the weights in the large language models, and they are updated, multiplied by this coefficient, whether it's advantage function, whether it's um, like estimated advantage versus some preference.
Okay. And the updates are all the weights, or is it using LoRa to do the update?
In DeepSeek R1, it's all the weights.
Wow. Okay. Right. Okay. Thank you.
Yes. Yeah, no problem.
Actually, I had a question I put in the chat if you can
Oh,
look
no.
at it.
Yes, let me take a look. If the model is not learning, how will go about choosing which RL to try in order? If we have very defined states to find an output well, Monte Carlo research working training. Um, okay, so the first question, if the model is not learning, you mean which RL algorithm to use?
Yes.
Yeah. So actually, among these different RL algorithms, the reason why they choose GRPO over PPO is not because PPO is not working, but because PPO is too expensive to learn because it needs to train this value function in addition to the policy model. And I'd say if the model really is not learning from the reinforcement learning algorithm, then it's probably there can be all different sorts of reasons. For example, whether the reward is defined correctly, or like whether uh the whether the search space is too big, and like the policy function is not is still like in a pure exploratory phase that is not actually outputting reasonable responses for the reward model to guide it toward. So like in general, reinforcement learning, if it's not working in the beginning, it could be really tricky to tune and figure out what goes wrong. And also, like regarding the second question, you have defined states to final output while Monte Carlo tree search work in training. So Monte Carlo tree search, it's not used during training, but more of inference time optimization. And by defined states, yeah, I guess it will work better just like in AlphaGo and AlphaZero. I'm actually for AlphaZero, I don't quite remember if it uses Monte Carlo tree search, but for example, for AlphaGo, it does leverage Monte Carlo tree search to do to get a better estimate and get better results.
Okay, thank you.
Yeah, no problem. Yeah, so yeah, for large language model, a lot of things are empirical, and actually it's costly to run tests because the models are so big. So even if DeepSeek works out quite well right now, or some other large language models work out quite well, a lot of times, like the researchers can only try out the methods on smaller models, try out the hyperparameters on smaller models, and there might only be very few chances or even one chance to run the full training on the bigger model. So does the rule we observe on smaller model apply directly on larger model? That's a question. And does the hyperparameters we use for smaller model, are they optimal for the larger model? That is also suspicious. That might not be true. But with these large models, at least for now, when the large models are getting trained, there is a little flavor of gambling or putting a bet on it that we think, okay, all these methods, it works out on small models. Let's give it a try on the big models. And even if it's not optimal, usually they work out fine. But it's true that they might not be optimal.
So if you have to downsize from a large model to a small model, and what is the, like if I have to come down from DeepSeek, what is the kind of size I should kind of first step down and see, and at what size it's really hard to get results or get training?
You mean to come down,
Because DeepSeek is pretty large, right? So trying to see how to use a smaller model to get at least some of the results. So how have you seen people use what size models they have come down to?
Yeah, definitely. So for example, in DeepSeek paper, they also discuss the distillation process where they use the supervised fine-tuning data generated from all this process, like you can call it a DeepSeek R1 pre. generate the supervised fine-tuning data, and run them on these smaller models. And they also get pretty good results on these smaller models. So these are like Quen 1.5B, 7B, Llama 8B, 30B. So I'd say as far as I know, like usually during experiments, like daily experiments, it's probably conducted on maybe 7B, 30B models, or yeah, 70B might be a little too large for daily experiments, but 7B or 30B models, they are good for experiments. And when you are actually considering deploying the model and using it for your own use case, like I want to run a model locally on my Mac, then yeah, like a 7B model or 30B model, they can give quite good results as well, and they usually fit into personal computers. Yeah, and yeah, just so you know, to estimate the size of the model, like because billion, it directly relates to gigabytes in computer memory or disk space. So if the model is using 8-bit quantization, which means one parameter directly maps to 1 byte of memory, then it means if you want to download a 7B model, it's probably 7 gigabytes of size. And to run it for inference, you would at least need about 7 gigabytes of computer memory. Yeah, that's one way if you want to try playing out these models locally, one way to estimate the size you need. And to do training, it needs bigger memory because usually during training, the model might not be quantized for the best quality. And you also need to save the gradients during the training process. Yep. Okay, sounds good. If that's all the questions.
Sorry, I have a very quick follow-up question on that. Does that mean if I have a 64 gigabyte Mac that I could run just for inference, I could run Qwen 2.5 32B?
Yeah, I think very likely. So 64 gigabytes of memory, right?
Right.
Yeah. Then yes, I think you can try. For 32B Quen model, there might be a few caveats. The first one is the quantization level.
Right.
The model is like BF16, then it's probably not going to fit. But if it's using 8-bit quantization or even 4-bit, then there should be no problem loading the model into memory. And during the inference process, if the sequence is too long, it might also run out of memory. But I think that's a good starting point to try. Also, sometimes Mac has this memory management that caps memory allocation for a task so that it does not impact the running of other programs. So,
Okay.
but
Yeah.
yeah, but I think you can give it a try, and you can probably find on Google or ChatGPT how to
Okay.
tweak the cap on Mac memory.
Okay, thank you.
So the BF16, right? That's 16 bits, right? Not 16 bytes. Am I
Yes,
right?
16
So
bit.
16, that would be 2 bytes, right?
Yes, 2 bytes.
So yeah, so 7 billion would effectively map to 14 billion, 14 gigabyte.
That's right. Yes.
Gigabyte.
Yes.
And the Mac, if it is 3024, it can take. Yeah. Okay.
Yes. Okay, cool. Great. Then we can probably end it here if there's no other questions. And thank you all for coming and for having a discussion.
And thank you very much.
No problem.
Thank you so much.
All right. Thank you so much, Chang, for such a detailed session. And I think people are good. And I will be posting the recording once I get it. And thanks again, everybody, for joining the session. And I hope you all enjoyed it as well. For now, goodbye.
Thank you, Dot. Bye.